はい。皆様、おはようございます。よろしくお願いします。I have been in Japan for a lot of the last 2.5 years working as a participating scientist in residence with the Akatsuki missions. There are about seven or eight of us working with the mission. Ralph Lorenz here as well is one of the participating scientists. And I thought it would be a good idea to come here and give a quick overview of some of the results of the Akatsuki mission, especially in the context of comparative planetology. Unfortunately, the team leaders weren't able to be here. Most of them are preparing for the International Venus Conference, which will be held in Hokkaido in 2 weeks. I'll also be there, but I'm young and a little easier to make all this travel. So that's a little bit of a warning that almost everything I'm going to talk about today actually is not my own work. So I will probably make a lot of mistakes, but I can help you get in touch with the people who will tell you, who will set you right if I misrepresent anything. All right, that's fine. I can use my fingers. So the other thing I want to mention is, I may or may not get through everything, especially now that I've gotten discombobulated here. So I'm going to give a quick summary of where I'm trying to get to with this. So if it's too long and you won't listen, the field of exoplanets, I think, will soon provide, and a lot of this we've already been hearing all week, so this isn't really, some of this is not new, but it will soon provide an abundance of varied planets to study, and whose evolution we want to understand. Today we know insolation, soon we will know atmospheres. Right now, Akatsuki is revealing a much more dynamic atmosphere of Venus, whose variability on all observed timescales is exceeding the predictions. For example, we're seeing a coupling of the surface to the upper atmosphere. We're seeing some interesting meteorological, maybe even Earth-like meteorological structures in mid-latitudes and equatorial latitudes. And we're seeing global scale variations in clouds and other constituents as well. I think an important takeaway that I've really starting to recognize, planetary atmospheres are complicated, ugly beasts. They are four-dimensional, or could even four-dimensional heat engines with numerous interconnected and coupled physical processes at work. And if you really want to understand these, you need to get the data necessary to understand these. And going about it piecemeal as we have for 50 years ain't gonna do it. Possibly this is the atmospheric equivalent of a sample return. I am talking about a lot of data. However, I don't think it's as complicated as a sample return. But I think it needs to be treated in the same way. And this is just, Venus is the ideal fulcrum by which all this can be leveraged, but I think there are definitely ways of applying this suggestion, the fact that we need more data about atmospheres from the planets, with regard to Titan, Mars, and Venus as well. So, Akatsuki's scientific goal was basically to do this, to try to build a four-dimensional picture of the atmosphere of Venus, and it was going to do this with a series of cameras at multiple wavelengths and a few filters, and also some radio occultation. This isn't a new idea. Basically, this is what we've been doing to try to study Earth's atmosphere for decades. This is the most recent example, the Himawari satellite. We have over a dozen channels on this, measuring different constituents of the atmosphere and different altitudes of the atmosphere and dynamics over time. Akatsuki was taking this idea and trying to apply it to another planet for the first time, and I think it did so very successfully. On one of the first 3 images that Akatsuki obtained after arriving, it made a brand new discovery. This is a long-wave infrared, so about 10 micron image of Venus, taken immediately after orbit insertion, and they noticed this huge planetary scale wave structure in the clouds. They noticed, at least initially, it was stationary with regard to topographic features on the surface. This is a feature at 60-70 kilometers tied to surface phenomena, despite 60 kilometers of atmosphere and 10 to 20 kilometers of cloud to try to get through. This is completely unexpected. However, observations the spacecraft had to go into commissioning phase, and so the next time they got a chance to look at this, it had disappeared, and they hadn't really learned anything about it. However, spacecraft has been there for several years, and we've been able to see this thing reappear multiple times. Always a stationary feature over topographic rises. We've started to see this at many different places. Just to zoom in a little bit, this is the same sort of thing. We can see the contours of topography at the top here. Also have found that they tend to appear most strongly at particular solar time. And so this is an indication of surface winds driving upper atmospheric winds or middle atmospheric winds, and tied to interactions with the sun. And so again, we're seeing a highly coupled three-dimensional structure of three-dimensional interaction in the atmosphere. We're seeing evidence of both climate and weather in the atmosphere of Venus. This has been studied through models. This is Tomás Navarro's work recently published just a couple of months ago, simulating these features with a GCM, actually identifying that, or at least finding that one possible explanation for these is basically a change in the near surface wind structure with regard to the topography, basically whether it flows around a mountain or over the mountain, depending upon the local thermodynamic conditions due to the solar heating. We also are seeing evidence of morphology in the mid-latitudes, which kind of resembles Earth morphology. Now, if we wanted to make this a little bit more accurate, this is actually a negative image, and so I've changed the Akatsuki image to a negative image. This is at 2 microns. And we can see a similar morphology. I'm not saying this is absolutely the same, but it's possible. But we're seeing possibly circulations. It's hard to really get a sense of whether or not this is actually what's going on, because in many of these cases we only have a couple of images before either the space it was out of view, or the atmospheric rotation had moved things out of view, or the timing was just bad. Next. We have also been noticing significant variations in the motions of the clouds at 2 microns. These are possibly suggestive of either mesoscale cyclones or mesoscale jets in the atmosphere, suggesting mesoscale baroclinic activity. These are fairly short timescale observations. These are just a series of images over a few hours and a few days, right? So these are just a few hours. So these are about 6 hours apart. Noticing significant changes in the wind speed, noticing the presence and absence of mesoscale jets in the atmosphere. So we're seeing an acceleration of the wind speed, or actually deceleration. Yeah, an acceleration of the wind speed here at about 10 to 20 degrees latitude, which occurred during this particular observation but was not seen at this time. Moving to even shorter wavelengths, if the team has compared wind speeds looking at 365 nanometers and 283 nanometers, both in the ultraviolet. 365 senses an unknown absorber in the Venus atmosphere. 283 senses mostly SO2. Obviously, there are clouds everywhere, and so this is also contributing. But what they have noticed is over here on the left is zonal wind, and this is meridional wind, so east-west and north-south. And they're noticing a detectable difference in the wind speeds at these two filters, suggesting that possibly this is providing more information about at what altitudes these particular features are located, which provides a little bit more help in terms of understanding, for example, what this unknown absorber might be, but then also helping us to understand where exactly the radiation from the sun is being deposited in the Venus atmosphere, because even though most of it is reflected away by the clouds, half of what actually is absorbed by Venus is absorbed basically at these altitudes. So if we really want to understand the energy balance of Venus, we need to understand what's going on there. This is actually from Venus Express. A glory was observed, and I encourage all of you on your flights home to look out your window, and hopefully the sun's in the right place and you're flying over clouds. You will see the same thing. This is a fairly small feature. It's only usually a few degrees in width, but it is an indication of fairly uniform cloud particles. This was seen from orbit by Venus Express, and it enabled the team to be able to provide more constraints on the properties of the cloud particles in the upper atmosphere of Venus. This was sought in the Akatsuki data. Initially, Akatsuki has a much larger apoapse, and so it's not possible for Venus to be small enough to see the glory in the clouds itself unless you're very near periapse, which is a very complicated observation to make. So they compared data at different times and saw evidence of a glory. Observations have been made at periapse more recently, and they are encouraging. I can't say more. So Akatsuki is taking us from the past of Venus multispectral to the future. And what is this? What are the lessons for the future? We've already seen things like this. We're looking at exoplanets. Right now, this is what we know. We know insolation, and so we know how bright the star is, how far the planets are, and that tells us whether we have icy water, or the possibility for icy water, or gassy water, or watery water. But as we heard earlier this week, atmospheres are very important to really constrain what the water is doing, for example, and everything else in the atmosphere. And we're getting close to being able to do this. This is recent work by Levy et al. We can start to measure atmospheric composition, and that will help to tell us whether or not these atmospheres really can support. And we had a talk recently actually exploring some of the parameter space for this. And I really like to talk earlier this week on the strike zone, because that's a two-dimensional thing. This is many dimensions, but prior to this year, the strike zone actually wasn't defined by video replays, and it actually evolved with time over the course of a game. And evolution of the planet is also key to understanding its habitability. This is a bunch of words, and I have only seconds left. So this is basically saying, in the current decadal, almost many of the questions actually point to trying to understand atmospheres in order to get to the bottom of what's going on. However, planetary atmospheres do not exist in a vacuum. Well, maybe they do, but the atmosphere is not an entire entity. There are other drivers. The surface in it, the interior and the surface also drives the atmosphere. And if we really want to understand planetary atmospheres, we need to get to the surfaces of the planets we can to understand how those have influenced atmospheres over their history. And this basically tells us we need to spend a lot more effort understanding the drivers of the atmospheres of Titan, Mars, and Venus in our own solar system if we hope to have any confidence in the predictions we're making about exoplanets in the future. Thank you.
So we have time for a couple questions. Anyone?
Okay, go ahead. Really enjoyed the talk. What kinds of, I know we're always thinking about future missions and Venus and how hard that can be, but what kinds of things would you like to see, or what kinds of things would you like to investigate on the mesoscale if you were to get a next Venus mission?
I don't even want to limit it just to Venus. I mean, I think if what we need is we were looking at Earth models recently, and the amount of data that goes into validating an Earth model dwarfs what we have now. It's because it's easier to observe the Earth than it is. I mean, we've got thousands of ground stations, and we've got hundreds of radiosondes, and we've had dozens of orbiting satellites. That's not going to be practical for any of these other planets, but that's the direction we need to go. So, being able to put a number of ground stations on Mars that are going to be long-lived and be able to tell us the evolution of surface meteorological conditions at a variety of places over long periods of time, that'll be necessary. We could do the same thing at Titan. Looking at Venus and Titan as well, I think Himawari and Akatsuki and GOES, these all tell us that, with an orbiting satellite, we can actually probe many levels of an atmosphere if we choose those wavelengths correctly. And we can understand, and if we choose the wavelengths correctly, and we observe for a long time. Because the thing is, if we look at a surface, we look at Mars. What was the big news about Mars in the last couple of decades? We looked somewhere, and we looked somewhere again. Things changed. That's the eureka moment in surface geology. Things are changing on the surface. With an atmosphere, changes. That's what an atmosphere does. If you go back and you measure the same atmosphere twice, you did not measure the same atmosphere twice. It just doesn't happen. Change defines these. And so if you want to understand how an atmosphere evolves, you need to observe over long periods of time. And I think what one lesson I think from this is we need to get away from this concept that, if you propose a mission that's more than 5 years, that's obscenely risky and there's no way in hell it's ever going to happen. Sorry. That's no way it's going to happen. You need to be able to you need to be able to propose missions that are going to last for a decade or several decades, because that's how long you need this data for.
Here, here. All right, thank you.